Hello and welcome to lecture 43 of the course Theory of Computation. This is also the beginning of week 9. So far we have been seeing decidable and undecidable languages. We saw reductions. We saw how we can prove some languages are undecidable using reductions. And at the end of week 8, I showed you this problem called post-correspondence problem, right? And I said that this is an undecidable problem, and the speciality is that so far the undecidable problems that we have seen has been very technical in nature, have been somewhat abstract. Does this Turing machine halt on the string? Does this Turing machine accept at least a language of this type, and so on, right? So it's not something that you could describe to a common man or like a school going child, right? However, post-correspondence problem is a very simple problem. The problem statement can be easily described to anybody, right? So the problem statement is the following: given a bunch of dominoes, right? So this is an instance. Is there a way to arrange these dominoes such that the top string and the bottom strings match? And the red part, this one is a solution for that. This is a match of the instance that is given over here. The instance has only 5 dominoes. Now, if you see the solution, the top string A B A B A B A B B A B B B A B B. So if the bottom string is A B A B A B A B B A B B B A B B, it's the same thing. The top and the bottom are the same, but of course the top progresses differently from the bottom. The bottom progresses quickly at first, and then later the top catches up. Some rules I have to mention. First is that it is not compulsory to use all the dominoes, right? So not all the dominoes need to be used. And 2 is that we could use some dominoes more than once if we need. There is no restriction on how many times we can use. And then obviously we can say the top and bottom strings match if we choose nothing, like an empty match. So the empty match is not usually allowed, because that will make every instance have a match, right? So the only 2 rules are, so we don't need to use all the dominoes, and we can use each domino how many ever times that we want. Okay, so this has a match that is listed here, and if you see all the dominoes is a domino that is given in this instance: A divided by A, B A B, B A A B B, B and A B over here, right? A B B by B, A B B B, then B A B, then A B B B, right? All the dominoes are dominoes given here. So another example is, does this instance have a match? The instance that is given over here. If you think about it a bit, you'll see that the answer is no, because in all the dominoes the bottom string is longer. So how many ever tiles that we arrange, how many ever dominoes that you arrange, the bottom string will always be longer, and it will continue to keep getting longer. There is no domino allows the top string to catch on later. So if you see the first instance, in fact the second instance is the same as the first instance, but the last 2 dominoes are not there, right? It's only the first 3 dominoes of the first instance that are there here. So here the bottom string is longer, here it gets even longer, here it gets even longer, right, till the 4th domino, and the 5th domino onwards the first domino starts catching up, right? But then there has to be some domino where the first domino is longer than the bottom. The top domino is longer than the bottom, so that the top can catch up, right? So here we have dominoes like this, where the top domino is longer than the bottom, and the top can catch up. However, here in all these dominoes, the bottom domino is the longer one. So how many ever dominoes you put together, the bottom string will always be longer. So this instance does not have a match. Okay, so these are 2 instances, and the language, the PCP question is, given an instance like this or like this, we have to determine whether there is a match or not. In this case, the first instance had a match and the second instance did not have a match. In this case, we could find that. But is there a algorithmic procedure or is there a standard procedure that we can follow and determine whether the given instance has a match? Turns out there is no such procedure and this problem is undecidable, right? So that's why this problem is interesting. It's a very simple problem. There is no Turing machine. There is whether the EQ-CFG or all CFG or any such things are not there. It's very simple. It's some dominoes and we have to determine whether there is a match or not, right? And it's surprising that such a simply describable problem is undecidable. Okay, so let's move towards the proof of the fact that PCP is undecidable. And in order to prove that PCP is undecidable, we are going to define a slightly modified version of the PCP problem. This will act as an intermediate step. Let's simply call it modified PCP, right? For lack of our imagination or whatever, let's call it modified PCP, short MPCP. So it's like a PCP instance, but with an additional constraint, where we say that it is an instance. So the instance is exactly like this. We have to construct a match where the top and the bottom strings match. But now whenever, so now I will give you an additional constraint. The additional constraint is that the match has to necessarily begin with the first domino, right? So that is the modified PCP, right? But with the additional condition that the match should always begin with the first domino. So the first domino should be the starting point, right? So in PCP there is no such constraint. I could put whichever domino first, right? Okay. So so now the way we will show that PCP is undecidable is that we'll show two things. We'll show that first we'll show that MPCP reduces to PCP and then ATM reduces to MPCP. So ATM reduces to MPCP implies that MPCP is undecidable. And since MPCP is undecidable, MPCP reduces to PCP implies that PCP is also undecidable, right? So together, these two together imply that PCP is undecidable, right? So this one implies that MPCP is undecidable, and once we have that MPCP is undecidable, this implies that PCP is undecidable, right? So let's see the first and let's see the first part. MPCP reduces to PCP. This is simpler. So given an MPCP instance, right, we have to reduce to a PCP instance, right? So MPCP, the match has to, so MPCP we are asking, is there a match starting with T1 by B1? Okay, so I'll call them T1 by B1 because so the divide, it is not a division, so it's not like, it doesn't mean divided by, but for want of a better word to describe this, I'll just call them T1 by B1. Okay, so MPCP instance means that the match has to begin with T1 by B1. Okay. Now we will create an equivalent PCP instance. Now if I look at this whole instance as a PCP instance, it need not be equivalent because in the PCP there is no constraint that the match starts with T1 by B1, right? So it could start with TK by BK, for instance, right? Which would not be acceptable in the MPCP instance, right? So we'll do something in order to force, so we'll construct using this instance itself, but we will force to begin with, the construction will ensure that a match will begin from T1 by B1 or the corresponding domino from T1 by B1. So we need to first define some transformations. So notice, so recall that all this T1, T2 up to Tk, right, and B1, B2 up to Bk, these are all strings consisting of lots of symbols, right? So let U be a string, okay. Now where U and U1, U2, etc. are the individual symbols, let's say that be n symbols, right. Now I am going to define three notations. One is star U, U star and star U star, okay. And where star is a symbol that is not there in any of the T1, B1, etc. right, T1, T2, B1, B2, etc. right. Star is a symbol that is not there in any of the these alphabet, right. So what is star U? Star U means that we start with a star, and before every symbol of U I am putting a star. So it's star U1, star U2, star U3. So just to give an example, if maybe I'll use a different color, let's say U is 0 1 1 0, okay, then star U is star 0 star 1 star 1, maybe I'll just, let's say it's 0 1 1, right. Star U is star 0 star 1 star 1, and U star is simply star after each symbol. So 0 star 1 star 1 star, right. There is no star to begin with. In star U there was no star to end. In U star there is no star to begin. And finally star U star has stars at the beginning as well as the end. So I have this star 0, star 1 and star. Okay, so the last one doesn't quite look like 1, so let me just modify it. So this is what I mean by star U, U star and star U star. So all of them have stars between each symbol, but star U has one at the beginning but not at the end. U star has one at the end but not at the beginning. Star U star has one at the beginning as well as the end, right. Now using this notation we will transform the MPCP instance to a PCP instance, okay. So this is the MPCP instance, T1 by B1, T2 by B2, etc., Tk by Bk. The PCP instance is the following. So notice that the MPCP instance, the first domino has a special position, right, because the match has to start with this. So this gets transformed to first star T1 on the top and star B1 star in the bottom, okay. And then we transform all the dominoes. So the first domino alone gets a special transformation, star T1 divided by star B1 star. Then we transform, then every domino gets a transformation. So let's see what the transformation is. So T1 by B1 becomes star T1 by B1 star. T2 by B2 becomes star T2 by B2 star. So there is a star at the beginning, star at the end. Tk Bk, T star Tk Bk star. Right. So this gets this transformation is made for everybody, T1 B1, T2 B2 and Tk Bk. And finally we add one more new symbol, that's a diamond, right. This is a diamond, to get a new domino which is star diamond by diamond, right. So the PCP instance has k plus 2 dominoes, where the original MPCP instance had k dominoes, right. Because the first domino gets a special transformation, star T1 by B star B1 star, then everything else like T1 B1 gets star T1 B1 star, star T2 B2 star and star Tk Bk star, and then finally a special domino to end things, star diamond divided by diamond. So now let us see what is the speciality here, right. So now the point is that, now look at this instance, this PCP instance. The only domino that we can use to start the match is the first domino here, because we cannot start with the second domino, because the second domino top starts with a star, bottom does not. Same the third domino, same with the Tk star Tk by Bk star, and same with the star diamond divided by diamond, right. So the only domino that we can use to start is this one. And then that is okay. So it starts with star T1 by star B1 star, and then we can append this or any other domino, whichever one suits us, right. So any star Ti by Bi star may follow it, but notice that with any of these dominoes, the issue is that the top ends with a symbol, original symbol, and the bottom ends with a star. So it is never, a match is never going to end over there. So because the bottom will end with a star, the top will not. So the ending thing, the only domino that can end a match is this one. So we need this diamond to end a match, because that is the only domino where the ending is the same on both top and bottom. So we end with this at some point whenever the rest top and bottom have matched up, and that constitutes the match. Now if you remove all the stars and diamonds, what is left is a match of the MPCP, with starting with T1 by B1 or T1 by B1, right? So the construction that we have created with the stars and diamonds basically ensures that we get an MPCP instance, but with a PCP match, but starting from T1 by B1. So that's why this corresponds to a match in the MPCP, where we start with the first domino, right? So the details, I have already told the details, but you can try to work out the details for yourself. The point is that because of the construction, the PCP instance will have to start with this domino, and when you remove the stars, it corresponds with match in the MPCP starting with this, which is what is considered a match in the MPCP, right? So whenever the PCP instance has a match, it has to necessarily start with this, and hence the MPCP also has a match. And whenever the MPCP has a match, it's straightforward to see that it corresponds to a PCP match, right? So that direction is easier. The reverse direction is a bit involved, so or only slightly more involved, and that I have explained. So this completes the proof that MPCP reduces to PCP, and it is very easy to make this modified instance, right? So the construction of the modified instance is easy, and the correspondence of the match is also somewhat straightforward, right? So now we have to show that ATM reduces to MPCP, sorry, right? So now this reduction uses computation histories. So now we will show that ATM reduces to MPCP. Given an ATM instance, our goal is to construct an MPCP instance. So given M, W, we want to construct an MPCP instance in such a way that M, W is an ATM if and only if the MPCP instance has a match, right? This is an ATM if and only if the MPCP instance has a match. In other words, M accepts W if and only if MPCP instance has a match, right? So let M be defined as Q, sigma, delta, gamma, and so on, right? That is standard Turing machine. And let the string W be written as W1, W2 up to Wn, the individual symbols, right? So now I am going to describe the MPCP instance, right? So the first domino is, the top is just a hash, and the bottom is hash, two hashes with this thing in between. And what is this thing? QS W1 W2 up to Wn. So in fact, if you observe this closely, you will see that this is the in fact if you if you observe this closely, you will see that this QS to Wn is the starting configuration of M on W. So basically we have this is the starting domino, right? As this is an MPCP instance, this must be the starting domino, right? This must be the starting domino. So now you can see that the starting domino has a hash on the top, and it starts with the hash, has a starting configuration of M on W, and then ends with the hash on the bottom. So the bottom is leading, right? And the top is trailing, and we have a starting configuration. So it's something like this. So if I scroll down a bit, it's something like this is what is happening, right? So I'm referring to this place. So when we just have the starting configuration or starting domino, we have something like this. If Q0 is the starting state and 0100 is the starting input content, then the starting domino gives us this. Now the goal is to construct dominoes such that what we will do is, I am telling you the high level goal. The goal is so now we will have to pick out dominoes such that here we get Q0, right, on the top. Right? Whatever domino we have to enter should give us Q0 here, otherwise it will not be a match. But then the matching thing here may be something else, right? So we'll ensure that by the time the top is filled out completely with a hash, this bottom will also get filled out, but what is filled out here will be the next configuration of the Turing machine, right? So the idea is the following. So the idea is, so this is a starting configuration, a starting domino. By the time the top, let's say, catches up, bottom would have moved one step. So when I say one step of the Turing machine, one step of the Turing machine computation, right? That's the idea here. So now when you move one step, and then when you match the top again, the bottom again moves by one step, and finally, so the bottom is always ahead, and at the end we need to somehow make sure that the top is allowed to catch up. And this happens only when we reach an accept state, and that's why the acceptance of the Turing machine corresponds to a match, right? So let's see how it happens. Now the next, so the first domino is this, right, that we have explained, hash followed by the starting configuration, hash on the top, starting configuration on the bottom. Then the second set of domino is this. For all AB in the tape alphabet and QR in the states where Q is not the reject state, if there is such a rule that delta QA gives RBR, right, it's a rule of the Turing machine, then we should add this domino. This domino is the added domino, right? So QA on the top and BR in the bottom. So why does it make sense? So let us see the tape itself. Let us see how the Turing machine tape is. Suppose the tape contains this 001 QA2, or suppose the configuration is 001 QA2. This means that 001 A2 and the head points at A and the state being Q, right? Now what we are saying is that delta QA is RBR, meaning we will write B and we will go to state R and move one step to the right. Right, so this is what delta QA is equal to RBR means, which means now the configuration is 001 BR2, which is what I have written over here, right? So now everything is the same, but I am looking at this part. Sorry, I am looking at this part, which is the part where it is distinct, right? QA in the top and BR in the bottom, and that I want to capture by the domino, which is what I have here. So this corresponds to all the moves where the head moves one step to the right. Next thing is for all ABC in the tape alphabet and QR in the state. So same thing, but delta QA is equal to RBL. Okay, so everything is same, but just that there is a left movement. Then we have this domino, where there is CQA in the top and RCB in the bottom. Why is that? So suppose we had 001 CQA2, right? What does it mean? This corresponds to CA2 with the head pointing at A and the state being Q, right? So now delta QA is equal to RBL, meaning you write B here, you move one step to the left and you go to state R. So this corresponds to 001 RCB2. So which is what I have here. So I have, this is the configuration that we started with 001 CQA2 and we ended with 001 RCB2. So here the difference is in these three symbols in the top and the bottom. CQA on the top and RCB on the bottom. So that's why we have this domino. So whenever we have a rule delta QA gives RBL, we should have this domino, like for all the possible C's. And whenever we have this rule delta QA gives RBR, we should have this domino. And we should have all, like for all such rules, we should have all the possible such dominoes. And in this case, for all the such rules and all possible C's, we should have all possible dominoes. Right? Now the rest of the dominoes are fairly simple. For any symbol A, right, we add this domino, where A is on the top and the bottom, right? So this is for the this is for the symbols that are same at the top and the bottom, like this one, right? 00 on the top and 00 on the bottom, right? Over here, etc. That's why we have this. And then the next set of dominoes hash on the top and bottom, right? And this is actually for hash on the top and blank hash on the bottom. This is actually for situations where that head moves to the right. Okay. Then finally, not finally, for the accepting state, we allow this. You have a Q accept in the top and Q accept in the bottom, or you have Q accept A in the top and Q accept in the bottom. Okay, so a Q accept in the top and Q accept in the bottom, or Q accept in the top and Q accept A in the top and Q accept in the bottom. So these are the dominoes where we allow the top to catch up with the bottom. Right, so and this happens only when we have accepting state in the top. So when basically what is happening is that the accepting state is kind of absorbing the nearby symbols. So this we write for all possible symbols A. And finally we have one more domino, which is this Q accept hash hash divided by Q accept. And this we will see when we work out the example, we will see that this kind of acts as the final step, right? And the idea of all this is that if M accepts W, or if MW is an ATM, there is an accepting computation history, and an accepting computation history gives us a match for the MPCP instance. If it is not accepting, then there is no match, because we need the accepting state for this absorption to happen. Okay. So perhaps maybe I think the simplest thing is to work out an example and see how these rules, right now it may seem like some arbitrary rules defined based on some Turing machine, some set of symbols and transitions. Let us see how it works out, right? Now let us see. So now here this means that Q0 is seeing 0. So let us define some rule. Let's say the rule was delta Q0 0, right? So it is in states Q0 reading 0. Let's say Q3 let's say 2 right. Okay, so Q3 2 right means that we should have this rule acting up. So we should have the domino Q0 0 on the top and 2 Q3 in the bottom, right? That domino will be there by the second rule. So you can verify that this domino will give us Q0 0 divided by 2 Q3. So now since to avoid confusion, I will try to alternate the colors. So the second domino will have Q0 0 and 2 Q3. Okay, so this is in red. Now the next domino, I could just use 1 on the top and 1 on the bottom, and 0 on the top and 0 on the bottom, and 0 on the top and 0 on the bottom. And then let me use hash on the top and hash on the bottom. Okay. Now let us say there is let's say another rule, delta q31 is delta q31 is, let's say, q7 I don't know, q7 5r. So this corresponds to a domino q31 on the top and 5 q7 in the bottom. So maybe I'll do one small thing. I'll try to delineate these things. So the first, sorry, it's a darker color. So the first one was this was the first domino. This was a, okay, it's too narrow to delineate, right? So that's why I have the color coding here, right? This is how it is, right? Now I will use something where I have two on the top and two on the bottom. So the symbols in the same color are the ones that match up, or that part of the same domino, right? And then I have q3 on the top, q31 on the top from this domino, and 5 q7 in the bottom, right? And now let me have 0 on the top and 0 on the bottom, 0 on the top and 0 on the bottom, and finally let me again have hash and hash. Right? So now again the situation is that the top is kind of like lagging behind, right? Now suppose it is in state q7 and it is reading a 0. Suppose delta q7 0 is, let's say it accepts from here. Okay, so qa, let's say 1, and let's say right. Okay, and if that is the case, then we would be q7 0, and the bottom will have 1 q accept, right? So let's now, so 2 will be 2 here and 5 will be 5, and now q7 0 will be on the top, and the correspondingly here will have 1 qa, okay, and finally we have a 0 here and a 0 here, and finally we have we match up the hashes, right? So that's the situation now. So maybe I'll just do one thing. We need to move to another line to continue this. I'll push this down so as to make up space. So now the situation is that right, I have, let me just carry forward this part, the highlighted part, because that is a place where the bottom is ahead. So I'll just write that here. Sorry, 2 5 1 qa 0 hash, and yeah, that's where we are, right? So now we could use some, like we could use 2 here on the top and 2 at the bottom, 5 on the top and 5 on the bottom, 1 on the top and 1 on the bottom. Which is all like single dominoes where you have 2 2 5 5 1 1, and then I will use this domino a q accept by q accept, right? So or I will use I will use this one. So for instance, I can use this domino, q accept 0 by q accept, right? So I will just say q accept 0 on the top, and the bottom will be q accept, right? And so let's see what happens now, and then let's say I use hash and hash. So notice that so far the entire configuration in the bottom was leading, but now now again the bottom configuration is leading, but now the bottom configuration has slightly shrunk. Basically this particular domino allowed the top to catch up. Now we may use this again. We may use the domino, let's say 1 qa by qa, right? So let's see. So first we have 2 5 1. Maybe I'll use another color. Before that, let me just use another color for this as well. Okay, I'll use 251 here and 251 here. Sorry, not 251. I'll use 25 here and 25 here. Oh, sorry. Two 5 1 here, 25 here. Then I will use 1 qa in the top and qa in the bottom. And then again close it with a hash. And now I can use 2 on the top and 2 in the bottom. And then I will use 5 qa in the top and qa in the bottom, right? That is also allowed, because anything can go in the top and bottom, it's just qa, right? So now maybe I should carry forward. So this is the carry forward thing to be carry forwarded, 2 qa. Let me do it in the next line. I won't need that much space, so I'll have 2 qa hash right. So now I can use a single domino where 2 qa is in the top and qa is in the bottom, right? Such a domino is also available as per this rule. 2 qa is in the top and qa is in the bottom. And now again I can close it off. So now this is the situation. The bottom is just leading by hash qa. Now let us see if I can use this one. Hash qa, it is leading. So we cannot use this right now. So first we need to put a hash symbol, I think. So we'll put a hash here and hash here. And now the bottom is leading by just qa and hash. So now we can close off things by using this qa hash hash and bottom just hash. So I can close off things. Maybe I'll use a different color. qa hash hash in the top and bottom just hash. Right. So basically this is this domino. So now you see how we have managed to use. So now the match is complete, as you can see, right? So now the match is complete. Right, so now it should be clear. So what is happening here? We started off with the starting configuration leading in the bottom, and the top had empty. And whenever the top made, like we caught up in the top, the bottom made one step ahead. So bottom, it is corresponds to the configuration of the Turing machine, one next step. So the top is one step behind in the terms of the configuration of the Turing machine. And this continues. The rules are designed so that this continues till there is a point where the bottom gets an acceptance. And once we have an acceptance, basically then these rule number 6, right, the dominoes in rules number 6 will start to become useful, basically the accepting state can absorb the nearby characters. So that slowly allows the top to catch up. So initially we had this here 251 QA0 in the bottom. So we started off with this extra in the bottom in the second line. So now 251 and the QA0, the 0 is eaten by the QA, right? So the next time we have just 251 QA, and then the 1 gets eaten by the QA. So the next time we have 25 QA, and then the 2 gets eaten by the QA. So now next time we have 2 QA, and finally, sorry, 5 gets eaten, and then we have the 2 also gets eaten. So finally we have QA and then hash, and so the bottom is just leading by QA hash, and then we just put the domino 7 QA hash hash divided by hash. So this domino, this is the last domino. Maybe I'll just highlight the last domino. This finishes off things. Right, this finishes off things. So, and if we do not get to accept, we will never the bottom will never be, sorry, the top will never be able to catch up, because if you can see, the only places where the top is allowed to catch up is when we have an accept state. So two things should become very clear, that whenever there is an accepting computation or the accepting computation history, it results in a match. And second, if there is no accepting computation history, or if there is no acceptance, then the top can never catch up. So this completes this, or that is the reasoning for this argument over here. M accepts W if and only if the MPCP instance has a match, right? And it's also important that this be viewed as an MPCP instance and not as a PCP instance, because if we view it as a PCP instance, if we do, or in other words, if we do not insist that this be the starting domino, then there are many matches. I could just have one tile hash and hash in the bottom. This single tile is a match, right? Only empty matches are the only thing that are not allowed. This is allowed, right? So that is why it is important to view it as a MPCP instance, and that completes the proof that ATM is reducible to MPCP. So right, that shows that MPCP is undecidable, and we have already shown that PCP or MPCP reduces to PCP, so that together implies that PCP is undecidable too. So there you have it. It's a very simple problem. So given some tiles and dominoes, is there a match? This simple looking question, this innocuous looking question, is undecidable. There is no algorithmic procedure by which we can definitively answer this question, right? That sounds very surprising, but that's a fact, right? So we first reduced MPCP to PCP by putting the stars. From the MPCP instance, we created a PCP instance, and we've ensured that the PCP instance can only start off the match from the first domino, right? That's how we did the reduction. Then for ATM to MPCP, we used computation histories. We created dominoes in such a way that the first domino, the top is empty and the bottom has the starting configuration. And then whenever we fill out the top to match up with the bottom will have advanced one step of the computation, right? And this goes on, this lead of one step in the computation is maintained throughout till there is an acceptance. And once there is an acceptance, the style number 6 allows the top to catch up by absorbing the symbols near the accepting state. And finally, we close it with the tile number 7. But then that is available only on acceptance, right? So that is the, maybe I'll just also highlight this side. This is the starting configuration here, starting domino here, and we end with this domino, and that completes the match. And it's now fairly clear that the MPCP instance as a match if and only if M accepts W, or in other words if and only if MW is in ATM. That completes the reduction, and hence we can see that PCP is undecidable. That's all I have for this lecture, and these are some rules that I have just written down anyway. One is that empty match is not allowed, right? Otherwise it is meaningless. 2 is that repetitions are allowed, and 3 is that we need not have all the dominoes in a match necessarily, like we could skip some dominoes or mini dominoes also, right? All of these I have said earlier, but I just noted it down, and that completes the proof that PCP is undecidable, right? So it's a problem that is undecidable, but it's a very, very simple problem. So that is the surprise, and that is the contrast as well, because so far all the other undecidable problems were somewhat technical and abstract, whereas this is very, very simple and easy to describe. And that completes the proof that PCP is undecidable, and that's also the end of lecture 43. In lecture 44 we will just see a brief application of the fact that PCP is undecidable. So see you in lecture 44. Thank you.